Welcome everyone, my name is Sher, and I'm going to be giving you this webinar today on reverse engineering complex surfaces and how to choose the right approach for different situations. So, a little bit about me. I have a degree in industrial design from DAP that I got back in 2011. And since then, I've been focusing on all things 3D printing, laser cutting, CNC milling, 3D scanning, different kinds of product design, and of course, reverse engineering. Now, during this webinar, I encourage everyone to ask as many questions as they'd like. I love the interaction. We have a questions box as part of the GoToWebinar interface over on your sideboard. So if you want to put those questions in there at any time, I'll try to work those in. So, today, we're talking about the problem of complex surfaces. So with most reverse engineering, like this engine here, it's pretty straightforward how to go about things. You know, which surfaces were extruded, which ones were revolved, add fillets here and there. It's not a mystery as to how the part was made. So parts like this are pretty straightforward. However, oftentimes you'll come across other surfaces that are more organic. They have a lot more curvature to them. And we need to figure out how to appropriately reverse engineer those kinds of surfaces. So now what do I mean exactly by complex surfaces? So these are, as I said, they have compound curvature and they're not easily made with basic tools like extrude or revolve. They're also, not primitives like cylinders, planes, or cones. And they're probably originally made with something like a loft or a sweep operation, or perhaps some of the newer, more organic modeling tools you're seeing these days. So as an example of the type of thing I mean, I have this electric screwdriver handle. So handles are a great example of this because they often have some interesting curvature to them. They're not straightforward shapes. There's a lot going on. And not only is there some complicated curvature, there are also some details like those lines in the grip that sometimes we might want to include in our reverse engineered model and sometimes not. So to go into this a little bit greater detail, here is the model in DesignX, and I'll be jumping back and forth throughout my presentation. So if you want to see anything in greater detail, please let me know. But yeah, here it is. This is the raw scan mesh cut off from different parts of the screwdriver, and I'll be showing you different ways to go about reverse engineering this shape. So, generally speaking, there are three main options for reverse engineering surfaces like these. We have the auto surfacing approach, which is very, very fast and easy to do, and also very accurate, but doesn't allow for easy modification. Next, we have lofting, which is sort of the other end of the spectrum. It's a lot slower. It takes a lot to make a lofted surface, but it is very easy to modify and tweak, and can be even be done so parametrically. Finally, we have the mesh fit or single patch workflow. Now, this is sort of in the middle. It's faster than lofting, but not as fast as auto surfacing, and it is easier to modify than auto surfacing, but doesn't give you as much control as a lofted surface. So with each of these three approaches, we're going to be going over a few different things. First off, what are the outputs of each of these operations? Some advantages and disadvantages of these different approaches, an example of good applications for each one, and finally, what's involved in all of these? Do you need to prep the scan mesh at all? What steps need to be done to create the actual features? And finally, if you can refine the features afterwards, what that looks like. So let's get into it. Workflow number one, auto surfacing. So auto surfacing is a tool that a lot of reverse engineering softwares have, such as DesignX, where the software is basically you hit a button and it figures out how to create a NURBS B-spline surface, or rather a network of them, that completely covers your selected scan mesh and turns it into a CAD surface. So let me show you that in the software. So here's my mesh, and here is my auto surface. So if I turn off my mesh, you can see it's pretty much the exact same shape. And if I turn on my accuracy analyzer, you can see that it is almost completely within spec. So this is plus or minus 0.004 of an inch. If we look closely, I think there's a single spot up here that's a little bit higher than 4 thou, but for the most part, you can see it's very, very accurate. So advantages, very fast. It's usually just a single button and then the computer just does some calculations and then you get a beautiful output. As you saw, very, very accurate. And it's easy. You don't need to do a lot. You can teach someone how to do this workflow pretty quickly, and then they can just be churning out auto surfaces all day. Downsides, of course, are that you can't omit any details. So you saw that auto surface has every single little curve in that scan mesh. If there were some manufacturing defects, those would be included. We couldn't do anything about that. Also, if there are some deep crevices or holes that the scanner didn't catch, those holes will be in your auto surface as well. They won't be filled. Now, and also because these surfaces tend to be very complex, features like surface offsets or thicken operations don't tend to work. They often fail. And of course, as I said, it's not really parametric or adjustable. The output is the output. So why would you want to use this option? So the best example of this, of course, is anytime you want to do any sort of fixturing. So this is really where this approach shines. You will often have workpieces that you need to fixture as part of your manufacturing process. And even if you have the CAD models for your part, if let's say it's a large injection molded part, the output is going to be slightly different from the CAD model due to things like shrinkage and warpage and sinks and the like. So having another CAD model that accurately reflects the real world shape of the part for your fixture is going to be a lot more helpful than the idealized pre-molded version of that part. So you can then take that model and do things like make these custom soft jaws for this part where it wraps into every little surface nook and holds the part super securely. This is also a really great approach if you want to make aftermarket additions for something. So for example, I see this used a lot in automotive where people want to make custom speaker pods for inside of a car. Often they want to wrap these around the columns of different parts of the car and make them blend seamlessly. And capturing those surfaces that they can then make something to fit tightly around is really helpful for that. Now, workflow, as I mentioned, very straightforward. You don't really need to prep the mesh. The feature creation is just a few clicks and you're done, but there's no refinement. So the output is what it is. But other than that, very helpful, straightforward workflow. So next we have lofting. So lofting is when you have, as you can see, just a single surface made by connecting a number of sketches. So we have a bunch of construction planes, sketches that are cross sections of the mesh on each of those planes, and then those are created with a loft. A loft feature is used to connect all of those sketches into one surface. Now, advantages are that this is very parametric. Everything about it can be driven by different measurements or equations. You can move planes around, you can tweak each individual sections, and so it's very, very adjustable. Unfortunately, it also takes the most work. It's very slow. You have to create a bunch of different construction planes, create individual sketches on each plane, and then create your lofted section. Also, because of how lofts work, it's often difficult to have a result that is both accurate and smooth. So by default, if you have a loft with a smaller number of sections, it's going to be smoother, but you won't necessarily capture every bit of curvature of the model. On the other hand, you can have lots and lots and lots and lots and lots of sections with very highly detailed sketches on each one and have something that is super accurate, but then it's not going to be as smooth as that simpler version. So it's hard to get both of those at the same time. So would you want to use this approach? Usually it's when you want to make some small changes to a shape. Now, in this case, I made pretty obvious changes just to show you what I was trying to do, but these finger bulges could be very subtle if I wanted them to, because I have that very small amount of control. So if I go back to DesignX, I'll show you what that looks like. So actually, before that, let's go over into the workflow so I can explain a little bit about what you're about to see. So with lofting, unfortunately, you often need quite a bit of mesh prep. So a surface must either be just a single surface or an enclosed volume throughout the entire shape. It can't go from a volume to a flat surface. And I'll show you what I mean in a minute. It also can't have any holes. If there are holes, the lofting operation will fail. And then all of the details that, if there are any details you don't want to include in your final model, you have to take those out of the mesh. You can't, it's more difficult to remove them from the loft after the fact. So let me show you the different versions of that. So here is the original mesh, and here is the mesh with the basic preparation for loft. So you notice I've closed up this area here, because if we tried to mesh this shape, all of these sections throughout here would be enclosed loops, but towards the top here, they would just be partial U's, and you can't have that kind of transition. They have to either all be enclosed shapes or all partial shapes. So that's why you want to close up any holes like that and on the bottom. So this is the sort of the bare minimum that would be needed. More likely, you'd do something like this, where you defeature all of the parts of the mesh, all of the details that you don't want to include. So we got rid of the button, we got rid of all of that surface detail on the grip. It's just the curvature of the grip itself. So then we can take that and make a simple loft. So if what this is, if I bring this down a bit, is we have several different planes and each one has a sketch on it. And so each of these sketches is then combined to create the final loft. And what I did is I actually went in and made a modified version of this. And so if I want to make any sort of tweaks to this, I can just go back. It's fully parametric. So I can go back to, say, this sketch here, edit that sketch. Oh no. There we go. I can grab some of these spline points, move them in, maybe make this bulge a little less aggressive. Finish that sketch, and now that change is reflected in my final lofted surface. So I can do that with any of these sections and make modifications that way. So that's why I say it's the most adjustable, the most parametric. You can even go in and add more sections if you need. That's a little more tricky, but it can be done. More easy is to actually just take existing sections and move them around. So finally, so yes, as you saw, feature creation, lots of construction planes, lots of sketches. You can create guide curves between sections if you like, but that's not necessary. And then you create your loft feature. And then finally, as I mentioned, refinement, very straightforward. Now, finally, we get to single patch surfacing. I'll be honest, this is my personal favorite, and that's because it's sort of the Goldilocks approach. It combines the accuracy of the auto surfacing, but with more adjustability, more control, more similar to the lofting approach. And so that's creating multiple NURBS patches. And so instead of a network of them, you're creating individual patches here and there, and then trimming them and patching them together with a little more purpose. So advantages and disadvantages of this are that, as I said, it's much faster than lofting, and you can omit features without editing the mesh. So this is very key. With both lofting and auto surfacing, if you have areas that you want to omit from your result, you have to modify the original scan mesh. With single patch, you can see, because you're creating these single patch surfaces from any arbitrary selection, you don't need to defeature your mesh at all. You can leave it exactly as it is and then just not have the elements that you don't want to be in your final model included in your selections. It's as easy as that. Because of that, these can be very, very accurate, almost as accurate as an auto surface. With the advantage of they're usually smoother. So where if you need to thicken a surface, this is going to be a better approach for that. Now, some downsides are is that this is a little more, this requires a little more forethought and intentionality, whereas lofting and auto surfacing, you're throwing inputs at the function, tweaking some parameters, and then getting an output. Whereas with single patch, you need to actually look at the surface with a little more care and say, okay, where do I want my edges to be? How do I want to capture different areas? And put a little more forethought into it. Also, individual surfaces are not parametric. So similar to the auto surface, those individual patches, once you create them, they are what they are. You can't really tweak their shape like you can a loft. However, you can, because you are trimming these surfaces and cutting into them with other tools, all of those types of features can be parametric. So you still have some parametric control over how the part comes out. So what's an example of a single patch application? Something like this. As I mentioned, anytime you want to do some sort of skin type feature where you're creating a surface and then thickening it, single patch is going to be your best friend. And it's also going to give you, nice, smooth, and accurate results very quickly. So for example, here, and I'll just show you this in DesignX, we have this little button guard, and I'll just turn my mesh back on so you can see that. So this is where I took my my single patch surface here, and then thickened it, trimmed it up, and added this button guard feature, so that if you wanted to avoid accidentally hitting that thumb button there. But just as an example of the type of thing that could easily be made using this tool, and because it's made using that single patch surface, it very snugly conforms to the existing grip. So this is a great example of a good application. So how does single patching work? As I said, you don't need to prep the mesh at all. All of the magic is in the feature creation. So what you're doing is you're creating single patch surfaces. That are basically square bits of NURBS B-spline surface with as much detail as you choose. You can sort of choose the resolution of detail capturing for each individual surface patch. And then those are going to be sort of stretched around the parts that you want. And you create as many of these separate patches as you think is necessary. And then you can create other tools to trim those surfaces so you're just using different surfaces for certain areas. And then you can join them using a few different tools. So for example, if we look at the single patch surface I have here, this was created with just 2 single patches. So this one and this one. And if I show the mesh, you can see that I tried to trim them along this line of curvature that's built into the handle. So I wanted to sort of separate them there. And then you can also see that they're not quite touching. There's this bridging area. So one nice trick you can do is build in this gap between 2 trimmed surfaces and then use a loft operation to smoothly transition between them. So if I turn on my accuracy analyzer, you can see it's not as accurate as the single patch, but it's pretty good. Some of these so here it's just a little over 4 thousandths low. Right on this loft, it's not very high at all. 6 thousandths. So as you can see, very, very accurate cell, even though it's nice and smooth. And then furthermore, I idealize this a bit by then trimming it right down the middle and then just mirroring the surface. So this side is going to be a little less accurate because it's just a mirror of one, and you always have slight variation in the real world. But it's still pretty good. It looks like it doesn't get much above 15 thou. And well, let me just show you how I trim this together. So I have some different, let me go back and show you some of my tools. So here we had some different surfaces I used to trim this. Here's one surface I used to cut one of my single patches into this shape. Then here's the other. And so these are just simple sketches that I extruded, and those sketches are fully parametric. These extrude operations are parametric. And so if I wanted to tweak where that line was, I could just go in, edit those sketches, and adjust the shape of my part that way. So we still have a lot of adjustability, even though we don't have quite as much control as we do with a lofted operation. And that's what I have for you. So if you have any questions, please put them in the question box. I'd love to hear from you. If you don't think of any now, but think of some later, my email is jsher@goengineer.com. Feel free to drop me a line. I'm always happy to answer questions anyone may have. Also, since we're at the end of the webinar, if you want to go ahead and unmute yourself and ask questions that way, that is totally fine. I will hang around here for a few minutes in case anyone has any questions. Just in case anyone needs to run off, thank you all for joining us. I really appreciate your time and letting me share this bit of knowledge with you, and I hope you found it useful. Dan, great question. So Dan asked, any reason you can't close the sections manually instead of having to close the surface? No. So you can absolutely go in and close each. So when he's talking about the lofting operation for creating surfaces, and instead of closing off this area in the mesh, leave it open, and then when you create your cross sections, just add some lines to close them off that way. You can absolutely do that. One reason that I chose to edit the mesh is I think it's a little faster to quickly close a hole in the mesh than to edit each individual cross section. Another reason is within DesignX, there's actually a loft wizard that will create those planes and sketches for me. So if I have a mesh that will generate a valid output at the beginning, that wizard will work better for me. But that's absolutely a valid way to approach that. So Drew said that for lofting, his experience has been that guide curves are extremely important for good results, but their location at which they intersect each sketch is also key. Yeah. So in many programs, guide curves, in order to be used, they have to have not just a point where they intersect each cross section, but they have to have a specific relationship in the sketch that clearly defines that there's a Pierce relationship. So that, and when you have those kinds of relationships, when you go back and edit your cross sections, those can easily be broken. So that's why I try to stay away from those when I can get away with it. I did not use any guide curves in this particular lofted model. I just used cross sections. All right. Well, if there are no further questions, I'll go ahead and wrap this up. Again, thank you all for joining us, and have a great day.